In the mixed-dimensional periodic Anderson model for U2, a combination of unidimensional conduction electrons and 2- or 3-dimensional pholectrons is proposed to simulate the band structure of U2. The model exhibits antiferromagnetic fluctuation and spin-triplet superconductivity. By varying the pholectron level delta F, the model demonstrates a transition from two-dimensional rectangular-shaped Fermi surfaces to mixed-dimensional ones, which is consistent with LDA plus U and LDA plus DMFT calculations for U2. The model also shows that the hybridization parameter VFP affects the shape of the three-dimensional Fermi surface and changes the nesting property. The spin susceptibility is calculated using the random phase approximation, RPA, revealing antiferromagnetic fluctuation with the wave vector around 0, pi, 0. The Eliashberg equation is solved to investigate superconductivity in the model, indicating that the model exhibits spin-triplet p-wave superconductivity. The superconducting transition temperature is determined by the condition lambda equals 1, where lambda is an eigenvalue of the linearized Eliashberg equation. The numerical calculations are performed for a 64 × 64 × 64 lattice and a Matsubara frequency cutoff of NF equals 1024. The results suggest that the interplay of magnetic fluctuation and superconductivity in U2 is essential for the origin of the superconductivity, as indicated by various experiments suggesting ferromagnetic criticality. The research paper discusses the application of a mixed-dimensional periodic Anderson model, PAM, to understand the magnetic fluctuations and superconductivity in U2. It focuses on the parameter dependence of antiferromagnetic and ferromagnetic fluctuations, and how they relate to superconductivity. The model is able to reproduce both types of fluctuations and their coexistence, which is consistent with experimental findings. The study also examines the relation between the wave vector of magnetic fluctuation and the symmetry of superconductivity, concluding that spin-triplet p-wave superconductivity is stable and can coexist with antiferromagnetic fluctuation. This is a characteristic property of the mixed-dimensional PAM, which differs from the 1 plus 2-dimensional PAM. The paper suggests that the model can be extended to include spin-orbit coupling, magnetic field, and multiple orbitals and sublattices, and that further studies are desirable to identify multiple superconducting phases under pressures and/or magnetic fields. In the research paper, the authors discuss the recent developments in the high-purity crystal growth of U2, which has led to a second era of experiments in this field. The quantum oscillation, thermal conductivity, and NMR night shift measurements have revealed behaviors consistent with the order parameter D equals kx plus k plus case, similar to the B phase of 3He. This order parameter contains kx and kz orbital components, realizing strong, weak, topological superconductivity in the absence of a three-dimensional Fermi surface. The authors appreciate helpful discussions with several experts in the field and acknowledge the support from JSPSKAKENHI. They utilize Fermi surfer to describe the Fermi surfaces in this paper. The paper reviews various studies on U2, including those on quantum oscillations, Fermi surfaces, and superconducting phases. The authors highlight the recent discoveries of a quasi-2D Fermi surface and electron hole tunneling in U2, as well as the detection of a 3D Fermi surface and strong topological superconductivity. Theoretical models, such as the 1 plus 2-dimensional periodic Anderson model, are also discussed to understand the correlated normal state fermiology and topological superconductivity in U2. The authors emphasize the importance of further studies to elucidate the mechanisms of superconductivity and the role of metamagnetism in U2. The paper also presents a comprehensive list of references, covering a wide range of topics related to U2, including experimental and theoretical studies on its superconducting properties, Fermi surfaces, and normal state behavior. Overall, the paper provides a thorough review of the current understanding of U2 and its potential as a topological superconductor. The research discusses the mixed-dimensional periodic Anderson model, focusing on the 1 plus 2-dimensional variant. It compares and combines results with the 1 plus 3-dimensional model to reveal general properties. The 1 plus 2-dimensional model has a zero-hopping integral along the kz direction, with other parameters identical to the 1 plus 3-dimensional model. Magnetic fluctuations and superconducting instability are studied by varying the pholectron level from 0.05 to 0.13. The study includes Fermi surfaces, spin susceptibility, and superconductivity, highlighting differences and similarities with the 1 plus 3-dimensional model. In the 1 plus 2-dimensional model, antiferromagnetic fluctuation dominates over a broader range, and ferromagnetic fluctuation appears at a higher pholectron level. Superconductivity is classified by irreducible representations, showing a stable state change from spin singlet to spin triplet at around increment f equals 0.08, associated with the antiferromagnetic to ferromagnetic crossover. The gap function and eigenvalues of the Eliashberg equation are also discussed, providing insights into the nature of superconductivity in this model.